Perfect. Well, good morning, good afternoon, good evening, depending where you are. Thank you a lot for attending our annual event. Before we start, I just want to run two short videos of our sponsors, starting with the main one, that's actually the Geoscience and Remote Sensing Society.
Good morning, my name is Paolo Gamba and I am the president for the year 2020 of the Geoscience Remote Sensing Society. Okay, so first of all, what is a scientific society? What is GRSS? So a scientific society is a group of scientists, researchers and practitioners with common interest and common framework for building a community. In our specific case, we are people who are dealing with theory, concept and techniques of science and engineering as they apply to remote sensing of the Earth, ocean, atmosphere and space, as well as the processing, interpretation and dissemination of this information. So what are the activities of the IEEE Geoscience and Remote Sensing Society? Well, we have a number of applications. We support conferences. We have professional activities. We have a number of information service and technical activities and education activities as well. We are a global community, which means that we are arranged around a large number of groups of people that we call chapters all around the world. We have currently more than 90 chapters all around the world. As a result, GRSS disseminates premium science by means of its three main journals, which are the Transactional Geoscience Remote Sensing, the Geoscience Remote Sensing Letters, the IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing, but we have also a magazine, which, by the way, has a very, very important role. We also provide opportunities for the different communities, like, for instance, the community working on image analysis and data fusion. We also sponsor community-driven events, like the very successful Earth Vision workshop, but also the SpaceNet Challenge data challenges here, which is organized by SpaceNet. We support also community-developed tools like the DESE website, which is Data and Algorithm Standard Evaluation website, and also activities related to RFI observations. So we also facilitate and connect. We have a number of activities at in our main conference. We have the so-called TIE events, but we also organize different events related to connection with companies, industries. We have a number of activities like for young professionals, for women in engineering and in geoscience and remote sensing. And we share our knowledge on hot topics by means of distinguished lecturers and industry speakers. We have also a number of educational activities. This is one of them. This is basically, let's say, one of the many different small educational videos for kids that we have in different languages, but we have also, in addition to that, a number of webinars, which are also for people who are not kids, about remote sensing in different languages as well. We offer continuing education by means of webinars, which is especially important and useful in this situation where we are not able anymore to move around the world as we were in the past. So we can support continuing education of students and young professionals through conferences, journals, our magazine, webinars, and so on. We can promote capabilities of the different communities, algorithms, data set by means of the data fusion context, by means of dedicated events at our conferences, by means of the industrial distinguished lecture or industrial speakers. We help connect companies and young motivated people by means of the young professional event, by means of student grants, by means of the TIE forum. And we make the different community of Earth observation practitioner and researcher be aware of their and your topics of interest. So GRSS is actually a community of communities where we could together share and promote ideas, systems, and data set. We can meet with other communities and gain from their perspective, and we can build different collaboration to learn more from each other's and to come together in conferences. Thank you very much, and I hope you will enjoy this summer school and all the interesting topic and talks that you are going to listen during these days.
Wonderful talk from Professor Paolo Gamba, the current president of the Geoscience and Remote Sensing Society for 2020, this year. And I have another short video from the International Society of Photogrammetry and Remote Sensing, ISPRS, Student Consortium, led by Cheryl Rose Rice.
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the 6th edition of the IEEE GRSS Young Professionals and ISPRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISPRS Student Consortium. We are the official representation of the youth to ISPRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision-making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called Spectrum, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the general assembly for our members, a student night, another summer school, and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
Wonderful talk from the ISPRS Student Consortium, and showing how important it is to be a member of a scientific society. This enables actually us to make events like this. I would like to invite Professor Edson Aparecido Mitishita from the Federal University of Paraná. Mitishita, thank you a lot actually for accepting our invitation. I would also like to invite Camila Viana. She is a PhD student from the University of São Paulo, right? Yeah, exactly. And also our lecturer, Petra Helmholz, from the Curtin University in Australia. I don't know if I pronounce it correctly.
Perfect.
Perfect. Well, we will start then our lecture. I just would like to read some profile. Let me just check here the note. Sorry for the delay. Petra Helmholz is a senior lecturer in photogrammetry within spatial science at the Curtin University. And her work includes teaching and research. Her research is focused on applications driving research using photogrammetry in areas of health, agriculture, heritage mapping, and engineering, as well as underwater photogrammetry. She is the national chair of the SSSI Remote Sensing and Photogrammetry Commission, also an associate editor of the journal Photogrammetric Engineering and Remote Sensing, co-chair of the ISPRS working group I-10, and coordinator of the Bachelor of Surveying degree at the Curtin University. She won 5 awards, with the highlights being 2016 Curtin University Commercial Innovation Awards for Deep Water 3D Imaging, 2017 Asia Pacific Spatial Excellence Award in Education Development, and 2019 the Western Australian Spatial Excellence Award as an industry award for the project Kleine Face. Well, Petra, thank you tremendously actually for accepting our invitation. Please, the room is now yours.
Thanks a lot for this very lovely introduction. Much appreciate this. And before I start, I want to wish everyone, if you're placed in Australia, good morning. If you're, I believe for the majority of the audience, good evening. As mentioned, I'm based in Perth, Western Australia, and I have already Friday 8 a.m. So it's a very, very exciting opportunity to talk to you. And why this year was difficult, this year enables also this kind of events. And it's a big pleasure to talk today as part of the summer school, also looking at the lineup. I mean, my supervisor from the university in Hanover, Franz, was one of the presenters, so it's a very, very exciting opportunity. I was asked to prepare a talk about UAV remote sensing, and when I looked to the lineup of speakers, I believed that the deep learning, image segmentation, and classification was covered to a very high level and quality. That's the reason why in my talk I will focus more on how do you get to an image or also image which you then can use for the AI. Before I start, I want to acknowledge the traditional owner of the land I am today. It's a Watcha Noongar people here in Perth, WA, and I want to acknowledge their custodians to the land. And I would like to extend my acknowledgement of country to all of the other traditional owners around the globe. All right, so let's get started with the talk. So as mentioned previously, I have tried to put a presentation together which covers all of the important steps you have to follow in order to get to a product author image which you then can use for AI. So my background is surveying, as you could hear during the introduction. So I try to focus on the geometric aspects and all of the aspects you need to follow in order to get to a good product at the end. So something which allows you to do precise and accurate knowledge. They can derive accurate and precise knowledge. All right, so I start with different platforms. I will keep this rather short. I have in my appendix an overview of all of the different platforms. So I'm happy for the presentation to be shared, so you can look to all of the details, just introduction. With the different platforms, we have lots of different camera systems and components, so I will try to review them as well as ways of how to capture data using the UAV platforms. The majority of my talk will be focused on the data processing. Main reason is that's where the magic happens in order to derive a good quality products. And then I will finish my presentation with a conclusion. All right, let's get started with the different platforms. And so the first chapter, the platforms, is a very introduction, on the introduction level. Overall, my talk is aimed for YPs, so if you're PhD students, and so I hope even if you're a researcher, that my talk maybe has some components which are new to you. The first part, I'm pretty sure, will not be part of it, but I included it for completeness. All right, so which kind of platforms are available? With UAVs, we have two big groups. The first one are the fixed-wing UAVs. So I've tried to show a couple of them on the right side. We have the Gatewing UAV, which I think is not available anymore, but still commonly used. Then we have the Trimbles and the EBs. So fixed wing meaning we have fixed wings, and the most main characteristic of those UAVs is you have to operate them autonomously. So you normally can't take over menu control. Because the UAV is mainly gliding, they can stay in the air much longer. So the normal flight time is around 1 hour, compared to the more common rotary blade drones. It's a very long time, because they don't need much energy, because majority of the time they're gliding. The camera is built into the belly of the drone, and because the body is custom made, while the number of cameras you can actually use for the drones is quite limited. Also, the camera is in the same body. There's no gimbal available. It's just in the same body, no gimbal available as the engine, meaning that any vibration from the engine will affect the quality of the image. So what they actually do, I will try to describe it. The drone flies, they turn off the engine, the drone starts to sink, that takes the image, and then the drone starts to fly again. Yes, that's the fixed wing. One more important part is that because they're very sensitive for winds, movements, so it means I do not always fly nadir. There's a bit of sensitivity to winds, and normally have to fly them in a much higher overlay than 60-40%. I will come back to the wind issue and the overlay a bit later in my talk. All right, just as example, that's a gate wing flying at 100 meters height. And what you can see there is one of the ground control points which we placed on Sandford Rock. All right, more common are the rotary blade UAVs. They're self-launching. They can be operated using apps. They can be done they can fly autonomously, but you can also take over the menu operation. Regarding fixed wings, what I forgot to mention is they look actually like eagles. In Australia, they're attacked quite often by eagles, the fixed wings. Whereas the rotary blade, because they don't look like a bird, they're normally safe. They still sometimes get attacked by eagles, but not as often as the fixed wings. Because we need much more energy to keep the drones in the air. The flight time is much shorter. It's normally between 10 and 20 minutes. That's the disadvantage. The advantage is that the flight is much more stable. Because normally they come with a gimbal, we can control the capturing of the images much better. And we don't have any, the gimbal can compensate for wind or other issues as well. And another big advantage is why you have lots of more drones available. And the payload overall is much higher as well, meaning you can put not just cameras on them, but small cameras, but also digital SLRs or laser scanner heads. The most common one is a DJI Phantom and all of the other DJI series, but there are other companies like Leica and Trimble around as well who offer rotary blade drones as well. Just some two images of the Mavic 2 and a Phantom 4. Same flight heights. Looks slightly different because the focal length of the camera is slightly different, but also you can see that the quality, I'm not sure if you can see it through the live stream, but the quality of the Phantom 4 Pro image is much better. Why? Because the camera is a better camera. And if you want to achieve a good products at the end, good author images, well, to have a good camera is very important. All right, just very briefly about flight operation. So we have 3 degrees of freedom. So we have the movement around the direction the plane flies. So we have the roll, the rotation around X. We have the rotation about Y, which is the pitch. And we have the rotation around Z, which is the yaw. So basically the flight direction. If we have a quadcopter, what we have a number of propellers. So one in the diagonal direction turn the same direction, and the other 2 turn anti-clockwise. So 2 turn clockwise, also to turn counterclockwise, and we can achieve the different changes around the X, Y, and Z axis by basically powering up some of the motors and reducing the speed of others. If you have 4 propellers and one of them fails, means your drone will come down, because you need at least the minimum is 4, so 2 clockwise and 2 counterclockwise. That's the reason why some of the very big ones, they have more propellers, not just to have to lift a higher payload, but also to land the equipment safely in case one of the engine fails. The fixed wing have a normal component of a plane. Some of them maybe only have a radar. Some of them only have aileron, but normally the same components. And by us using the radar and the elevator and the aileron, we can achieve the changes in X, Y, and Z, and the change of altitude. All right, so let's come to the components which are important to create the ortho images, which are the cameras and the other components. So normally I took the Phantom as example, but you can find the similar sensors on the majority of the drones, because most of them, or the majority, if you do photogrammetry or remote sensing, are operated autonomously. They all have GPS or GLONASS or any kind of GNSS, so Global Navigation Satellite System, for navigation purposes. Sometimes they're built into the body, sometimes they're built on top, but the majority of the drones which are suitable for remote sensing will have GNSS. The GNSS is not good enough for landing because of the GNSS error of up to 3 meters. That's the reason why they use normally ultrasonic sensors to assist for landing. So the ultrasonic sensors focusing downwards, but there are also normally a few of them facing forward and backwards, just in order to avoid any obstacles and not to crash into trees or other obstacles. Drones normally come also with pressure sensors. The pressure sensors are used for if they're facing into the flight direction, for finding the speed of the drone. It's much more precise than using the GNSS components, and some other pressure sensors internally, which are also used in order to help for the height positioning. And drones normally also have gyros or tonometers installed as well, which support the navigation of the drone. How all of the sensors work together will be completely different a lecture, and I believe that one of the other presenters covered this aspect already, so I only want to repeat briefly which sensors. What sensor is for my talk the most important one is the camera, and the camera can be used for positioning, but the majority of the time it's not used for positioning. There are some optical flow and methods which become now available where this can be done as well. That's an ongoing field of research, but for the standard drones you can buy off the shelf. That's normally it's only used to capture the data, not actually for positioning or flying. All right, because of the limited payload of the drone, we are very limited also with the camera systems we can use. And if you look up any kind of literature, if you want to do precise and accurate modeling, if you have a better camera, you can achieve a better result. The cameras which are built into the drones, they got very good in the last decade, even the small ones. They allow actually to create very nice and precise data. But just have in your mind, if you need a specific quality, then you need a better camera. And the bigger camera, what's important is mainly the size of the sensor. And I will review that during the talk later on as well. Because most of the drones do not allow to take any camera on board, they are often customized designs, and the opportunity for you to change over cameras or even the lens is very limited. It's possible, but very limited. The majority of the cameras built into the drones are red, green, blue cameras, and if you want to perform remote sensing, what you often want is multispectral cameras. So you want to have infrared and red edge as well. Some of the drones allow to have such cameras on board, and some of them even also allow thermal infrared, but those cameras or those drones are not anymore the low budget or low cost drones. They can become then quickly a bit more expensive. Yes, the majority of the cameras built on the rotary blade drones have a gimbal, which is very good in order to create good quality images. Compared to, for example, the fixed wings, but again, the fixed wings, the big advantage is you can cover much bigger area. You maybe have to take more images, so you can, if there's a blurred image, it doesn't matter because you have enough other images of this area, but yes, a gimbal, of course, is advantage. Lots of the cameras built into drones offer to be operated as a still image. So you just take a single frame, another single frame, or as a video mode. The video modes often have something called a rolling shutter, meaning not the whole frame is updated, but only part of it is updated. If only part of the image is updated and we try to get all of the different frames, what we need is a good geometry. But if you only update half of it, what we basically do is we chuck all the geometry out of the window. That's the reason why if you want to, sometimes you have to operate in video mode. Okay, don't get me wrong. That's especially, you could hear that I do lots of underwater photogrammetry. So sometimes you have to operate it. If you can, try not to, just because you can achieve a better geometry. You can reconstruct the geometry better. I mean, you get overall a better quality outcomes. Just a small overview of different cameras. So the Zenmuse series are the one which comes with the DJIs. Then we have Canon and Sensefly for the RGB, but then we have also multispectral images, which includes the red edge. This list is not completed. That's just to give you a couple of examples. All right, I mentioned let's have a close look to some of the cameras. While in the appendix you have all of them, I just choose the Zenmuse X series because that's the one which comes with the most commonly used DJI drones. You can see the different models, and the important part is basically line number 2. That's the sensor size. And you can see that if you go from left to right, that the sensor size increases. If the sensor size increases, then we can normally achieve a better quality at the images for the reconstruction. Otherwise, the ISO sensitivity and so on, it's not that important. You should use not too high ISO, because if you have high ISO settings, you can introduce some noise, and we don't want to have some noise. But maybe you have to change it based on the light conditions you fly the drone in. And some of the majority of the lens come with the fixed aperture. A fixed aperture is normally of advantage because changes in the aperture, and especially when it happens during the flight, can impact the focal length. Therefore, can impact the camera constant, which you need for the calibration of the camera. All right, just to cover some of the multispectral aspects as well. One example is the Parrot Sequoia Mica Sense now, which has not just the RGB sensor, but also have built-in green, red, near infrared, and red edge. So this camera is installed in addition to the normal camera of the drone. As you can see in the picture on the bottom right. So it has its own little installation platform, gimbal, and is connected to a GPS and light sensor, which is placed on the top of the drone. So the position of the Sequoia drone doesn't come from actually the drone itself, but from their own little GPS sensor which is installed. It is a bit of a challenge because the RGB camera which is installed in the Sequoia camera is not the best resolution. The resolution of the camera installed on the drone is normally better, but it's very difficult to calibrate. You would have to calibrate the offset between the GPS built into the drone to the Sequoia camera from the GPS built into the drone to the internal camera, and then also the GPS from the drone to the GPS from the Sequoia camera. So there are lots of things which you would have to calibrate, which is done if you have airborne photogrammetry, but which is not always it's very tricky to do for operating the Sequoia on a drone. Also because due to the gimbal, the position of the perspective center keeps changing all the time. So while it can produce very nice looking images, which are suitable for example, vegetation mapping, there are some challenges which the majority of the standard softwares, as far as I'm aware of, have solved to the level which is normally required for the different applications, but not to the level which we are used to in photogrammetry. Just a couple of examples. So it's the RGB which comes out of the Sequoia. Then we have the red edge, which is especially important for vegetation and crop monitoring. We have the green, so you can see the difference between the different channels. Then we have the red edge, which is very, just red. Red edge was the first one, the reds. And then we have the near infrared. And well, if you have red, near infrared, red edge, and the bands, you can then not just create a normal digital surface model, which is the standard output out of an RGB sensor, but you can also then create your false color images, and you can then calculate all of your vegetation indices which you're used to, and that's just the example, the NDVI. Very important is you have to calibrate the sensor, especially if you want to calculate the NDVI and you want to compare the NDVIs of, for example, vegetation between time point 1 and time point 2. You have to make sure that your data is properly calibrated, meaning that, for example, a value of 0.5 NDVI from the epoch 1 is actually the same in epoch 2. So with the Sequoia, you normally get, you have to perform a radiometric calibration. You have to do this before you fly the drone. So you have this panel which is shown on the bottom, which has a specific where the reflectance is well known, and by taking the images of with different bands of this panel. Internally, the camera tries to calibrate it itself. It is repeated for 3 different times with different exposures in order to avoid saturation or under saturation. So why it has to be done while if you have a cloudy day, if you have a sunny day, the different light conditions all will impact the reflection of the crops or the vegetation, and careful calibration is required. I think it's still an ongoing field. I know a couple of researchers who really look into the calibration of the multispectral cameras which can be installed on drones. It's not that straightforward. especially if you want to find very subtle differences in order to, for example, analyze which kind of treatment has to be applied to the crops. There's one thing which is very important to consider, and if you fly the multispectral camera, is that the focal length of the Sequoia camera is different to the focal length of the drone. So why is it important? If you do the flight planning using an app, what you have to nominate is the drone, and then automatically the software normally picks the focal lengths which are required for the drone. Let's say, I think that was a flight planning for Inspire camera, 100 meter, and I nominated the overlap, I think it was 80-60. So what you can see, based on the software, based on photogrammetry, based on the software, you can, the basis between the images 35.8 meters. So that means the distance in which the images are taken within the flight path, with the Sequoia is 24.1. It's not a big issue because it's within the flight path. That means the Sequoia just takes more images. When it becomes important is the distance across the flight strips. Okay, so if you do the flight planning for your drone, you will get, in this example, told that the distance between the flight strips has to be 53.8 meters. In order to achieve the same overlap required for the processing of the Sequoia camera, you should have flown 36.2 meters. Right? But because the flight planning software doesn't consider that you want to take images with Sequoia, you will end up with images for the Sequoia camera with not enough overlap. If you have not enough overlap, you cannot actually create the ortho images. You can't stitch the images together. In addition, while the software tells you have a ground sample distance of 4.5 centimeters, the Sequoia will only give you 4.7 centimeters. So there's also a change in ground sample distance. So if you use the Sequoia camera, a very careful consideration for the flight planning is required. All right, data capture is rather short. First of all, I mentioned with the fixed wings, they are very sensitive to wind. So if the drone flies, the top image flies along and we have some wind coming from the side, meaning the plane will face into the wind in order to compensate for the wind. Because your camera is installed fixed into the drone, you end up to take not perfectly overlapped images as you want to capture in flight direction, but what you capture is something like that. So why here on the bottom, the way it should be, you can see the majority of the points will be covered with 3 or 4 or 5 images. If you have this configuration, no, not really. For example, a point which is supposed to be here, you can see it's maybe just covered by 2 images instead of 3 images. That's one of the reasons why you have to increase the overlap for fixed wings UAVs a lot. If you increase it, also means that you have more images, and more images means more processing time. Whereas with the gimbal, you normally don't have the issue. All right, what are the flight patterns? If you use software, while you can normally get offered the grid, you will learn in the second part of the lecture that the grid, just one direction grid, is not the best because you actually don't roll your camera, you don't turn it 90 degrees, meaning the calibration of the camera will be more tricky or maybe can't be done successfully. The double grid is therefore always better. What you will see in the last part of the presentation as well, that you should consider the circling around the point, or sometimes it's called orbit method as well. Then there are other methods as well, waypoints and asteroids and boomerangs and so on. But the main issue if you do photogrammetry with the drones is that you have in order to get good quality, in order to achieve a good quality of the calibration of the cameras, you have to use flight patterns which are maybe not available in the software you want to use. So maybe some manual flights are required. Manual flights can be tricky because it's actually not that easy to control the drone. So it's a bit of a balancing act. And yes, not all software support all flight patterns, which is the biggest challenge. Coming to the different softwares you can use, and that's just a quick overview. There will be many more rounds. We have a software which comes with specific drones, for example DJI Go and Motion. Some of them are suitable to do flight patterns for photogrammetry, remote sensing as well. Some of them not. You only can use them for menu flying. So one which are quite common in order to do flight planning for more photogrammetry focused application is drone deploy, LICT, and Pix4D capture, and so on. All of them normally work. The scary part is as soon as you operate the drone, you have to confirm that you're happy for the software to take over and that they're not liable in case your drone crashes. But that's something which is all of them have in common and something you get used to. Yeah, the cost can vary a lot, from free to quite a bit of money. So do good investigation which kind of flight pattern are maybe offered and options for you to capture the images. What is the standard that you basically provide with the flight height in which you want to fly? That's shown here, and then based on the flight heights and because the software know which kind of camera you operate, you get the resolution automatically. And then if you go in advance, you can also enter your side lap and front lap for the overlaps where you want to start, flight speeds, and so on. The majority of the flight softwares do not allow you to nominate if you want to take images in oblique view. But oblique views are very important for the calibration. So we'll come back to this aspect a bit later on. Some of the software have something called a survey mode. So survey mode means all images are automatically taken with an oblique view and that they're at the orbit at the end. So that the different producers have recognized it. All right, now the most important part of the presentation, which is the data processing. And the data processing workflow doesn't matter which software you use. The common softwares are Photoscan and Pix4D. Other softwares are 3DM Analyst and Australis, and they come from different backgrounds. So some of them come from the photogrammetry background, some come from the computer science background, but basically the workflow is the same. You load in all of the images, then you relative orientate the image. Sometimes it's called you create a sparse point loads, then type point generation, but everything it's the same. You try to find common points between the images and try to match them. Then you normally introduce a scale. So that's usually that you nominate a couple of ground control points. Scale can come from the positioning of the drone, so the GPS built into the drone, or from other just distance measurements. And after you introduced your control, you will have to calibrate your camera. Sometimes it's called you have to optimize your camera. But what's basically done in the background, you try to find the parameters of the interorientation. After you've found the parameters of the interorientation, you find the parameters of the exorientation. Sometimes it's done also together in one step. And normally for this step, you use something called the bundle block adjustment. Then after you find the parameters of the camera, so the I/O interior orientation parameters, and after you found the position of the drone, so the X orientation parameter of the different stations of the drone, then you can perform your dense image matching and then you can create your meshes, derive your ortho images, your volumes, and other information you want to get from the data. Most of the softwares allow a very automatic workflow, but please be cautious with that, because the processing of the geometry and all of the aspects are quite complex. So while it's easy to just press a button and you get a nice product, what I aim to do with my talk today is to tell you that there's much more towards it. All right, so there are lots of people around who do lots of work with drones and who has been much longer in the game, like myself. And now I want to talk about camera calibration, and I had the permission from Professor Clive Fraser to use a couple of his research for this presentation. If you want to listen to the full presentation of Clive, or I will refer later on to another presentation, just send me an email. If you're a student, you will be able to get codes which makes the presentation completely freely available to you. All right. Why do I have to calibrate my camera? So it doesn't matter which equipment you use in general, you want to make sure that you use calibrated equipment. If you are a surveyor and you have a total station, you make sure that the distance measurement inside of the total station is calibrated. If you do other kind of research, for example, if you use satellite images, you make sure that if you need calibrated images, you use the calibrated products which are provided by the different satellite companies. The same is with drone photogrammetry. You want to derive precise and accurate measurements from your camera, means you have to calibrate your camera. In order to achieve the best calibration results, you have to make sure that the images you take are actually suitable for performing good calibration. It doesn't always mean that you have to use ground control points, but you have to follow a couple of very basic rules which goes back to simple geometry. So if you want to achieve a good network geometry for self-calibration, you should make sure that you use a number of different images and that they are convergent network. Meaning that if you have perpendicular to your image of plane, that those meet at a point. You also want to make sure that you have an orthogonal camera roll. So we not just fly in one direction, but also across 90 degrees, so perpendicular. It is good to have a depth and object space. So if you have a perfect plane area, it's not the best in order to perform a calibration. It is good to have it, but it's not mandatory. In order to perform a good calibration, you need a highly redundant network. So it means you need at least 6 rays per point, meaning that a point in object space, a feature point, is captured by at least 6 images. You need a very precise measurements of targets. If you use targets, for example, if you use round targets, you can perform centroid fitting, so you achieve a much higher accuracy than just normal crosses. So you should try to have 0.1 pixel if you use targets and 0.3 pixel if you use a targetless structure for motion. Something which is important as well is that you have scale differences within the image. It means you have some areas which are closer and some areas which are further away, captured by the same image. Plus, of course, you have to keep your focal length stable, and your camera itself should be stable as well. And that's where some of the much cheaper cameras fail. All right, just a couple of examples, different case studies which Clive performed. So case study number 1 is a standard area block. And I think it's actually the data set which is provided by Pix4D as an example. So the block has overall 127 images, and Clive used Australis as the software, but normally the dimension of the number of feature points which can be created is around 180K. In this example, it was 180,000, so 180K. And 31,000 of the points were visible in at least 6 images, many of them in more than 10 images. So the RMS value, so the root mean square, which could be achieved, was 0.45 pixel, which is quite good. I mentioned that if possible, you should not fly in nadir, so you have variation of scale within the image. That was not followed here. However, there were was a strong change of the elevation in object space. You can see it's a pit. So one image basically could cover areas on the top of the pit and on the bottom of the pit as well. So you have the scale differences within different camera locations. Meaning in this case, the self-calibration actually was possible. Clive could produce very good results with low coupling, so correlations between the different I/O parameters. With I/O parameters, the interorientation parameters, meaning the focal lengths, the principal points offsets, radiance distortion, decentric distortions. All right, what is the flight number 2, the case number 2? That's something which I suggested for a long time to my students as well. So if you perform a flight, try to perform a flight in different flight heights, and also then within the flight heights that you have the double pattern grid. Meaning overall you have, so this image, the scale, which you can see is much different to the scale on the bottom image. The example here achieved 84 images with around 30,000 points visibly in more than 6 points, and many of them more than 10 points. And the RMS value which could be achieved was just 0.8. What the issue was, because while we had the difference of scales between the different flight heights, between the different flights, we didn't have much change of scale within the image. So for example, the terrain is quite flat. All of the cameras were looking nadir. That means within the image there was not much of a height difference, and because of that, it actually was very strong coupling and correlation between the principal distance and the camera station, meaning the focal length is highly correlated with the position of the drone in flight height. All right, so what does it mean? I have read many papers, and I have seen also many of my students doing that, saying photogrammetry is not precise because I have a height error of 2 centimeters. You actually don't have a height error of 2 centimeters. The main issue is that the focal length is not calibrated suitable for this area, because there's a strong correlation between the focal length and the Z. So there's actually, because you introduce an error with the focal length, what you get is a height error in the data you capture. So I've talked to a couple of people that what they do, they just do a rigid transformation then. So I have a couple of control points and do a rigid transformation to those ground control points. So they try to fix the issue afterwards, where it could be fixed by simply doing a better calibration of the camera. Okay, network number 3 is there's a building in the center which was mapped by a drone. You can see that all of those within a block, they're all parallel. So you have some convergency, but not the perfect convergency. That's not just always focusing to the center. Some of them, as you can see here, they're parallel. So in this case, we had 49 images, 50,000 type points were created, and 6,000 of them had 6 or more rays. Overall, the RMS is 0.3 pixels. So it's a very good RMS. So why is it very good? Because if you look, all of the images were taken oblique. So it means you have for each image points which are closer and further away. So you have the change of scale within the image. And that's the reason why actually the self-calibration worked very, very nicely. For this example, no ground control points were used. And the last one, and that's the one which you should aim for if you do a flight planning or capturing images of a drone, is you have some height separation for capturing the images, but you not just have your double grid pattern for capturing your area of interest, but you also have this convergent sample sets of images which you take in addition. So over here, 66 images were used to capture convergent images, and then 203 in an idea. Because of this very strong geometry, you can actually achieve very good results for the calibration, meaning overall you can achieve very precise measurements. So after listening to Clive's presentation, that's always the way I would suggest that you capture your images if you do a drone flight. If you don't do that, so if you just do the normal pattern, you will see something called the dome effect, and you will see this quite often. So if your area is flat, you fly nearly nadir view or nadir view, and you don't use ground control points, then something, how Clive phrased it, photogrammetry takes over. All right, what does it mean? We have the positioning of the drones from the GPS, normally 3 meters. In object space, we have lots of tie points. The matching quality of the tie points is within the centimeter range. We have around 100 drone stations, but we have around 100,000 tie points. So the least square adjustment tries to minimize the square sum of the residuals. That's what the least square adjustment does always. And in this case, by creating this kind of doming effect, it actually reduces the residuals. If you reduce residuals, the square sum of the residuals is smaller, and therefore gets a better output. Whereas, of course, we know that that's not true. So the doming effect is something you will see if you try not to follow the best practice. And the doming effect can be significant. So in this case, it's between minus 0.9 meters and plus 5.1 meters. So the difference here is nearly 1.5 meters. Okay, if you fix it to control, it should improve, but nevertheless, in order to create precise height information, please try to follow the guidelines I just tried to explain. Because if you have a height error, then if you create your ortho images, you get displacements based on height errors, and then displacement then can lead actually to wrong XY coordinates of objects you can see in your image, in your ortho image. So what does it mean photogrammetry takes over? And that's the last slide for the camera calibration aspect. Is, well, what do we have? We have normally image coordinates observations, or tie points, or sparse point cloud. We have this only in image space, so X and Y. And what we normally have 10 to 100,000 of tie points. They're created automatically, so we have lots of them. And because the image matching is very precise, the standard deviation is normally very small. So if you have a least square adjustment, they'll be giving a very high weight. Okay, then sometimes you have ground control points. We have a standard deviation of those ground control points in object space. Normally we have not more than 10 or maybe around 10 ground control points. And while here the precision is very small, so very accurate, a couple of maybe centimeter or two, those can be much bigger. Because if you pick it up with a GPS, with RTK, well, you have 3 centimeters. So while we have less points and the standard deviation appears bigger than the tie points, there's the one actually you want to fix the adjustment to. And then last not but least, we have the camera stations from the GPS. So depending on how many images we have, let's say between 100 and 1000, we have 100, 1000, and normally the standard deviation which comes with it are within a meter, because the majority of the drones use just standard GPS. I don't use RTK or PPK. Meaning the observation which has the biggest impact is the type points which we created. And therefore it will have the biggest impact to the least square adjustment as well. Okay, so we have to consider the weighting, and maybe also have to consider that even that our GPS within the drone or the ground control points we picked up are less accurate, we maybe have to give them a smaller standard deviation. So we give them in the least square adjustment a higher weight, and a higher weight means we can detect blunders, and we can use all of the magic which we are used to from least squares adjustment. Okay, so what it means, just to show you an example, so we have our standard flights which we shouldn't use, a network of 59 images, and we created in this case 21,000 points. The ground sample distance we could achieve was 1.6 centimeters in this case, and the type points which were created had the accuracy of 7 millimeters. Okay. Then we had the GPS stations, and they were assumed with 2 centimeters. We run Clive ran a free network adjustment, and what he did, he changed the values of the Z slightly in order to see if he can recover any kind of height errors which are introduced, which is shown in this table. So what we have here is the standard error which we give to the GPS. So that's 0.01. That's a real standard error. So that's what we can achieve with the GPS. And Clive artificially changed the standard deviation to something really ridiculous, but that means we actually give this observation a very high weight in our least square adjustment. Then he introduced errors to different control points. So we have an error of in the first run of 1.5 centimeters of one of the control points, and you can see that this is actually not picked up. So the RMS values we get is within a millimeter range. So the height error was not picked up because the type points, the precision of the type points, the number of type points took over, and we could not, or it's not possible to recover the error. Only if we put the weight of our ground control points to something very ridiculous. That's then when we can actually start to find why there's a height error actually 4.1. The same for point 2, we introduced in this case a height error of 2 centimeters. If you have a realistic measurement for our ground control point observation, we will not be able to recover again the error. Only if you put the ground control points to a very high weight, so very small standard deviation, it's possible to recover the errors. So what's the conclusion? Clive's conclusion is you have to rethink the weighting of your ground control points during calibration or least square adjustment. In order not for photogrammetry the type points to take over, it is sometimes required to actually weight to reduce the standard deviation of your ground control points by a lot. So it gives them a much higher weight as part of the least square adjustment. All right, so conclusion is for good network calibration, you require good geometry, and that applies to UAVs the same as to all photogrammetry jobs. Shortcuts should not be taken. It's very important to perform a calibration. If the field you want to capture is not suitable for calibration, it's good to have a comprehensive pre-calibration of the camera. Then the weights which introduce into the least square adjustment are the weights for the camera constraints for self-calibration. or for one of your ground control points, try to resync it in order to make sure that if you have errors, you can recover them, and photogrammetry in this case doesn't take over. And because you don't want photogrammetry, the number of type points to take over, sometimes it's actually smart to try to reduce the number of type points for your adjustment. All right, now we calibrated our camera. Everything is perfect. What are the next issues you can get exposed to? And that's based on my next couple of slides are based on Jason's talk. Jason is from Adam Technology, and he gave another webinar. And again, if you're interested to listen to Jason's full webinar, please get in touch with me. I will be able to provide you with a promotion code. All right, back to image overlap. So in theory, what you need are two images of a point, and you can create 3D information. That's the theory. You have two eyes. With two eyes, you can see in 3D. Lots of the structure from motion approaches, so the computer vision approaches, need more than two. They need at least three, or normally they try to aim for four or at least five. Okay. It's just a way of the methods work in the background, be able to apply Rensic and so on. So instead of capturing, let's say, 100 images, Pix4D, for example, wants to have at least 75% overlap forward motion and 60% side lap, and Agisoft is 80% and 60%, meaning that based on the methods you use in the background, you artificially have to capture more images. They have to capture twice as many in the flight direction, which is at least doesn't cost you battery power because it's within the flight, it just takes more images. But it also, with an increased side lap, means you have to fly more paths. If you have to fly more paths, it takes more battery power, so you maybe have to do a couple of different flights in order to capture the area. But the main issue is if you have more images, means you have to process them longer. It's not linear, it's all in square, meaning if you increase the number of images, the processing time will increase exponentially. Pardon me, guys, exponentially. All right. So what's happened if you don't have enough overlap? So what Jason found is that's what we can see. First of all, is we have a different flights strips which were flown by drone, and what you can see in black are the connections which were built between the different images. You can see that here between two flight strips, it was the software, in this case Pix4D, was able to find type points to connect those images together. In some areas, this didn't work because the side overlap was not big enough. And what you can see here are the arrow circles of your positioning of the drone, the arrow ellipses, and they increase a lot. So they try to force you to have lots of side overlap in order to have lots of connections. If you have lots of connections, then you have a stronger bundle adjustment in the background. But again, if you have more images, means it takes much longer in the processing. All right. That's when it comes to the overlap and sparse matching. But what is quite interesting is actually to look to the dense image matching, or the DTM or DSM generation. So after you calibrated your camera, and after you found the parameters of the camera and the camera stations of the drone, you normally want to create a dense point cloud. And there are two main methods which are used. The first one is least-square matching, which is again uses the gray values between images and performs tries to find the minimum of the square sum of the residuals between the different gray values. So it runs the least square matching algorithm in the background. Alternative is a dense matching, and the semi-global matching is one of the most popular dense matching methods. which doesn't use gray values of area, but tries to actually match pixel by pixel. So the least square matching uses an area and try to match the gray values of an area to the gray values of areas in different images. So what you need at least, you need the minimum area, and the minimum area you can define for many of the softwares are 4 pixels. Meaning you need at least 4 pixels in order to match them to another 4 pixels. If you only use 4 pixels, meaning you can't match 1 pixel to another pixel, you can only match 4 to 4 pixels. That means you have a smoothing, because you only use area towards area, not pixel by pixel, meaning you automatically introduce a smoothing to your dense point cloud. However, because the least square matching uses least squares, it's very accurate and can find mismatches quite easily and can isolate them. Whereas the dense matching methods will match and is a bit more sensitive for mismatches. So the least square matching doesn't work right up to the edge because it always needs an area. So if you are coming to the edge of a building, meaning some of the pixels will be on the bottom of the building, some of the pixels will be on top of the building, meaning you can't find a nice proper edge, it will be always a bit of a smoothing on edges. Whereas a dense matching can find the edge much nicer because they try to find single matches. Single matches also means it will run for a much longer time. Normally the software doesn't give you the option which kind of matching methods you want to use. It only tells you use the one I have. They normally don't tell you actually which ones I have. There are not many softwares where you can actually select which methods you want to have. One of the only one I'm aware of is the Atom software 3D Analyst. All right, so next thing is the semi-global matching. Because you try to match pixel to pixel, it takes a very long time. Okay, in order to recover time, what they do is they actually run the matching not on the highest resolution of the images. They actually run it on smooth version. So they create image pyramids with different levels of smoothness. So you have the full image contents, then they halve the contents, then halve it again. So we actually have a 1/4 of the original one, they halve it again. So you have 1/8 of the original one, and so on. So if you perform a dense reconstruction, use for example Agisoft, and you say you want to have the ultra high definition, or the ultra high resolution, it actually means that you use a full image. If you say you want to have a standard definition or standard resolution, meaning you only use half of the image, so you use a downsampled version of the image. If you say medium, which is a quarter, then you actually use a 1/4 downsample resolution of the image. So you try to capture very high resolution images, but at the end, because it just takes so long, you downsample the images to a low resolution. Yeah, that's something to consider. So what you can do, first of all, ask yourself, do you need the resolution? Do you need 3 centimeters downsample distance, or are maybe 6 centimeters good enough? Because then it means you can fly the drone higher. You capture less images, and means overall the processing will be faster. But on the other, and then which methods you want to use? Because do you want to actually use the full resolution of the images, and make sure that you use ultra high quality for the majority of the softwares. Some of them, they actually explicitly tell you what they do in the background. The majority actually don't tell you. You have to work it out yourself. All right, so that's the example of what Jason created using Pix4D of one of his flight he performed with the highest resolution. But if you look carefully, and I hope you can see it, you can see this concentric circles going away, and that's just something which can be reproduced quite easily if you have a flat, relatively flat surface and you use simple global matching. So it's just the effect or other dense image matching algorithm, dynamic programming, and so on. They're not real. They only are created because of the matching of the images, of the dense matching of the images. So if you reduce the resolution to medium, which means you use only a quarter of the original image size, well, you still can see lots of details, but you can see that the circles are actually even more emphasized. And then if you use the low settings, which is 1/8, again, there you can see again the circles, the artifacts, which are not actually in object space. They're purely created based on the matching method, which is used by the software. So if you finished your dense matching, basically have a very careful look to the point cloud which was created. It's important that you turn the texture off. If you don't turn the texture off, you hardly will be able to discover those systematic artifacts which are introduced in your data. And if you have them, well, then you have to do further post-processing in order to get rid of the artifacts. All right, therefore, if you try to compare different products, it's very important that you try to compare them in a fair manner, meaning you try to compare apples with apples, not apples with pears. So do they actually have roughly the same number of points? Do they have the same quality accuracy? Do they have the same ground sample distance? Not just to press a button and see how long it takes. Then also after you created the dense matching, it's important that you try to turn off the texture off and you look very carefully into to the product produced and try to find any kind of artifacts. What you always should do is use independent control. So please always leave some of the ground plot points behind and use them as checkpoints to indicate to check your quality. If you check your quality and the software provides you with a number, try to understand what this number means. Okay, because some software will provide you with the with the sum of the residuals. If you have a normal distribution, the sum of the residuals should be 0. So the sum of the residuals will tell you nothing. What you need is a square sum of the residuals. Because then if you have positive and negative, they don't average each other out. So make sure that you actually use the RMS, root means square error, not just the square sum of the residuals. And in addition, if you have a software, well, it's very tempting just to press a button. Just make sure that you understand the settings and the impact of the settings which they have to your final product. Yes, and always try to understand what the output means and how you can read the output. There are lots of cloud processing softwares available as well, where you upload your images to a web page and then you get a nice model back. But always try to have a healthy degree of skepticism in order to analyze if the results you get are good or not good. All right, so I only covered 2 of the talks. There are other talks as well when it comes to the webinars, which as part of the presentation you'll be able to access if you want to. If you want to establish your drone program, then maybe listen to Renée's talk. If you want to learn more about the camera calibration, what's important, then there's a talk by Clive Fraser. In Australia, we have lots of routes flying drones, so something I didn't cover at all during this talk. Please check with your national rules. If you want to learn more about the georeferencing techniques for drone-based photogrammetry and laser scanning, then maybe listen to Moshi's talk. If you want to learn more about the quality assessment, so the RMS and the square sum of the residuals and some of the residuals, try to listen to Jason's first talk. And then about the importance of ground control point and investigation of different camera platforms are other talks available. Each of the talks are 45 minutes, so I was not able to cover all of them, but if you want to learn more about any of the aspects, please send me an email. I will be able to give you a promotion code if you're a student. So I would, if you're undergrad or postgrad, doesn't matter, but as long as you're a student. All right, so what's the conclusion? My conclusion is there are many platforms, there are many sensors, there are many softwares for flying, there are many softwares for processing. There are lots of options and possibilities. Whatever pathway you take, make sure that you follow best practice. Best practice in capturing the data and the processing the images. It's very tempting just to press a button and you get a very nice looking product at the end. But try to actually assess all of the different steps and try to assess what the software produced. The photogrammetry is over 100 years old, so there's lots of literature available. You maybe have to do more digging, more research to understand all of these small aspects. But if you want to create a very good, high quality product because you need it for your research, you will have to follow it. So please resist the temptation of just press a button. And please spread the word to all of your friends and colleagues as well. And with this, I would like to finish my presentation. And I think there's time for some questions still left.
Wonderful and impressive talk, Petra. Thank you a lot. We have here some questions from the audience. Before that, I would like just to comment or to ask the importance of making a radiometric calibration. If you could just say in few words how important is actually to keep that and to perform, let's say, a good research or work.
The calibration, your radiometric calibration, is a whole research field by itself. It was done very extensively for satellite systems, because if you want to revisit the area, so if you want to change, let's say the crop. So we did some research together with agriculture department, and they want to monitor the crop health. So the NDVI for them is one of the indices they use in order to assess how healthy a crop is, and also to monitor the treatment. So after they applied different kind of treatments to the crop, they wanted to see if the health improved or not. So what was the impact? So if you don't have properly calibrated data, then means your NDVI it's not a reliable measurement which can be used for assessing the crop health, because the NDVI will maybe depend on the sunshine shining or not, but not actually the quality of your crop. I hope that answers the question. The thing with the satellite systems, all of the satellite providers put lots of research and efforts into it to make sure that it works. With the new available Sequoia cameras, I tried to put the effort in there as well. But if your research just depends on that, just double check that this actually works fine.
And what about the use of targets, let's say panels, with different colors, the white ones and black ones and gray ones, and the use or not of a spectroradiometer? Could you comment on that?
Yes, so what actually was done by my colleague David Belton, we exactly did this. We used the framework which was provided by the camera provider, by the vendor, and we put out a couple of targets ourselves, and we actually measured the reflectance of the different colors, and we found that there are a couple of issues with the camera itself. with the calibration procedure put into place. So yes, if your research depends on that, use control. And the control is use your panels, and if required, do the calibration yourself, so arithmetic calibration. And the person who is most qualified to answer how to do this with the Sequoia camera would be my colleague David Belton. So if there are any detailed questions, I'm more than happy to pass this on to my colleague.
Perfect. I would like to hand to Professor Mitishita if he has some comments, and then to Camila. And then we will start actually reading the questions from the audience.
Okay. Professor Petra, thank you very much for your very nice presentation. You are in the young professional and summer school talking. UAV technology open new possibilities to small company to open small company to extract geo information, metric information by photogrammetric procedures. Do you have a couple of recommendation, technical recommendation to young professional that you want to open a small company using EOV technology?
That's a very good question. And yes, more and more companies. So we did a survey actually to industry partners here in Perth last year, and 40% predicted that they would use drones in the next year. So that means the number of companies picking up using drones is a lot, and the number of new companies as well. So for the YPs, even if you don't want to have your own company, I think there are lots of opportunities around with established companies to get yourself into established company if you can show that you understand the workflow which comes with it. So one of my students, he did his thesis, his bachelor thesis about this topic, and he basically found the job straight afterwards and got the chief drone pilot of the company because he knew about the processes in the background. So if you want to have your own company, or if you want to be part of a bigger company in a new field, that's a drone pilot, make sure that you understand the processes, and then if you give the data to your clients, that you actually can be convinced that what you give to your client is the quality you promised. Okay, well, it's very tempting to press a button, and many people do that. And because many people do it, and they can do it much cheaper, so normally get the jobs. But I hope that they only get 1 or 2 jobs till the client starts to recognize, well, they promised me that, but they didn't give me that. So to put the effort in the first place, maybe short term, you will miss out on a number of jobs. But long term, I hope that you can establish yourself because you are seen as an expert. So you can deliver what you promise, and try to also understand your clients, because what I see often with the clients, they want to have 1 centimeter just because it's possible. Try to not educate, but try to talk to the client. Say, well, look, what is what you want to achieve? In order to achieve, we would need this accuracy and precision. In order to achieve that, I would have to do X, Y, Z. So try to run them through the work. Basically, not the complete workflow, but try to show them that you have an understanding of what they want, how they want it, and what's the best way to achieve it. That means please do not be a push button presser. So try not to just press the button in the software. Try to understand what's going on and be able to assess that what you give to your client is what you actually promise, and not just what the software tells you it is, but it actually is what it is. I hope that answers the question.
Okay, thank you very much.
Camila?
Well, thank you for the presentation, Professor Petra. It was very enlightening. I research and work with SFM photogrammetry. So I would like to know, it's a question similar to the one that Professor Edson asked. But I would like to know if you have any thoughts on how can we communicate more efficiently, both with students and companies, about the importance of this theory and the careful survey to produce good results. I ask this because I've faced some poor quality products, and also some questions like, why can I just buy a drone and do it for myself? Some clients do not fully understand the product that was delivered to them. So sometimes the conversation is rather difficult to explain why we need the theory and why we need to plan and understand the background process.
Yes, it's a big challenge, and I have to say, I don't have the answer to it, not the 100% answer, because even if I try my best to teach this to students, it looks like as soon as they go in industry, there's a reset button for some of them. So I think the one way to do this is to have events like today, and also to try to get to industry events to show what the potential is if you put in the extra effort. What the biggest challenge of us is, as our background is research. So as soon as we give presentation to industry, it's perceived as too complicated. So what we maybe have to learn is a little bit more talking in their language, but also try to explain them a little bit more of our language. And that's a very tough task, okay? And but I think for us, it's very important to do that, because otherwise, yeah, the push button solutions will take over, meaning that we basically failed in, I don't want to say education, because if you tell a client, I want to educate you about drone flying, that's not well perceived, because people don't want to be educated, because it means they perceive that they're dumb because they don't know the field, even that they have done this maybe for the last 10 or 20 years. So I don't want to say educate, but to tell them part of the story in a language which the client can see the value of it. So more from the client point of view. And just for us professionals to get more to the industry events as well, to tell the story a little bit. It's a very tough ask, but I think GRSS, but also ISPRS, they all have this on their agenda. So I hope if we work together that we can highlight that to our clients. But I understand it's a difficult task, and being in education as well, as I mentioned. When I meet some students again, I sometimes just shake my head and say, guys, come on, you had 2 or 3 lectures series with me. Can you remember what I told you? And yes, calibrate your camera. Right. And have you done? No. So that's one of the things.
Thank you.
Well, we have here 11 questions. So we have to, and we are running actually on time. Let's go, let's say for the first questions is from Ashar Ibrahim. He asked actually the basic difference between photogrammetry and remote sensing.
All right, I think I will answer the question different compared to everyone else because there's no definition for one or the other. How I see it as a photogrammetry is more the geometry aspect, to try to produce a highly accurate geometric model, and remote sensing is more the spectral aspect. So try to use different bands in order to derive indices in order to perform calibration of the reflectance of objects. So that's for me. Remote sensing, therefore, is very high resolution normally, and the remote sensing is, if you want to have hyperspectral information, you normally in very medium to low resolution range. But yeah, I would say one focus on the geometry and the other one focused on the spectral aspects, so radiometry. That's how I see it. And maybe the others in the audience can answer as well.
Perfect. I will hand the next one actually to Professor Mitishita.
This question that you put in the screen?
Yes, yes.
Okay. What would be the best configuration of RPS for detection of fruits and orchards and individuals people in the roads of giving seed?
Should I answer?
Yeah, if possible.
Sorry, I was not sure.
Yeah.
Well, first of all, I'm not sure about the people, and I think I will not comment on that. That's something which is against what I think and believe. For crowd management, I think it's nadir because you just want to see the number of people. But in order to identify individual people, I don't want to comment on that one. About fruit and orchards, I think it's a challenge to do this by drone because some of the fruit in orchards, such as oranges, they're not just on the outside of the tree. They're also inside within the canopy of the tree. So what you can do is you can try to capture the outside of the tree. So you use nadir view directions from the side, from each side and from above. So let's say 20% oblique, left, right, and nadir. And then if you have oranges or lemons, something which has a high contrast, I believe that you will be able to find the number of oranges and lemons without any issues. I have seen a couple of very nice AI approaches to do that. But then what you still have to do is to correlate what you can see to what is actually there. So to answer, so what is the best configuration for UAVs to detect fruits and orchards? I would say 20% oblique from each side. So you can see basically the side of the tree if you have 20% oblique. And nadir as well. That means you should be able to identify enough fruits, and because you have enough overlap between the images, you should be identify also which fruits are maybe the same fruit. But the next step is if you want to actually harvest, I want to have an indication of how many fruit are on the tree, you still have to correlate to what you can see to compare to what is there, if it makes sense. I have been many years of research also for vineyards available and apples and so on. So there are lots of resources.
Perfect. Camila, would it be possible to read the next one?
Yes, from Georgina. For UAV remote sensing, it's very important the calibration. Other aspects important take account about velocity UAV.
Well, velocity is what you try to achieve is you try to take images which are sharp. If you have a gimbal, some of them have a little bit of a forward compensation, or if you have that's not very common, but they start to do this. So they have forward compensation. So forward compensation means while you're flying, the sensors move backwards, so you end up to have sharp images. They're very expensive drones. The normal standard drones, you just try to have a short exposure time. If you have a short exposure time and you have medium speed, then you end up to have not blurred images. But what basically the rule is try to make sure that your images don't have any motion blur. If it's very bright, means you can maybe fly your drone a bit faster because your time can be shorter to capture the image. If it's darker, you maybe have to fly a bit slower. But basically, the main message is make sure that you have good quality images.
Perfect. The next one, Professor Mitishita, if you could read.
Okay. This question from Marcus Shimalski. Great presentation, Professor Petra. In your opinion, do you advise RTK or PPK system? What is the best accuracy that can be achieved with this system?
There are a number of RTK systems around, even DJI released for short-time RTK, so real-time kinematic GPS. You have your base station and then you observe your RTK. PPK is more and more pushing forward, meaning that the post-processing of the points. As far as I'm aware of the RTK as well as the PPK gets to accuracy level of 1 or 2 centimeters. So I don't have any practical experiences, but I think because the accuracy level is roughly the same, I believe that the outputs will be roughly the same. But again, I haven't had any opportunity to work with the drones yet. What I would like to emphasize is referring back to Clive Fraser's talk, even that you have maybe 1 or 2 centimeters, you have to see the standard deviations and the budgets of standard deviations as a whole within a least square adjustment. So not just the position accuracy of the camera, but also the standard deviations which comes from the tie points, the number of tie points compared to the number of drone positioning, which and the RTK and PPK. So even if RTK and PPK maybe only achieve 1 or 2 centimeters, you have to review all of the standard deviation which are part of the least square adjustment. So to answer the question, Marcus, I have not had any practical experiences between RTK and PPK. I know that more and more drones become available, and I think some good research will be soon required in order to see the impact. But overall, I want to emphasize that if you do a camera calibration or least square adjustment, it's important to review the whole error budget, not just the one coming from the RTK or PPK solution, but also the tie point matching quality and tie point matching quality. In general, you should be able to produce nice models with RTK and PPK, which are accurate and precise if you have a flight pattern which allow a reliable calibration of the system.
Perfect. The next questions from Meg. Is it possible to apply these methods for architecture, facades, buildings, constructions, and cultural heritage reconstruction? I guess that this is like, for the window, for details of the construction, the walls, and also the roof, and to keep the entire, let's say, reconstruction.
Yes. Well, if you want to especially do the architecture and facade and building construction, I would actually suggest to take a combination of drone mapping and terrestrial mapping. Terrestrial mapping, I think one of the first applications ever for photogrammetry was actually facade mapping. The pool of knowledge in this area is actually much bigger than what we have done for drone flights. So yes, it's possible. I would suggest to do a combination of drone and terrestrial. With the terrestrial, you can have a better quality camera. You can use the SLR. If you have a building, you can walk around the building. You have nice convergency. You have all of the things you should have. There's one issue, something called windows. The windows are shiny objects, and the windows can create mismatches. So I think you will be able to pick up lots of details on a building, but the areas of windows. Actually, if you have windows, if you can mask them out, because sometimes they reflect off other surfaces. and then you can see a tree and the the sparse matching, the feature point matching starts to match points in the windows compared to the object space. It can confuse things. If you have a shiny glass window, I would not try it with photogrammetry. I would use an alternative method, but photogrammetry for shiny big glass buildings, I think that's the wrong way. Otherwise, yes, I think a very good way to do it.
Yeah, who would like to read the next ones? Professor Michita.
This question from Patrio. Thank you for the very nice talk, Dr. Helmholz. What are the main difficulties concerning geometry and also the autonomy of planning swords of droning to cover large areas? Would that be a trend?
Talking about swarms of drones has been around for a while. Now where the drones have PPK and RTK, it becomes more visible because you actually can operate them as a swarm quite nicely. All right, what's the big advantage? You can cover a much bigger area, and especially I think one of the applications are health and rescue as well. I think the University of Queensland does a bit of research on that topic, but also other universities as well. In order to answer the question is what do you want to achieve? Okay, it's always what is what you want to achieve. If you want to achieve rescue mission, so you want to identify people in the field, so you know that you can send the rescue team to point A, B, or C, then I don't worry about calibration much, because you do not try to derive 3D measurements. You want to detect objects, and you can do that. If you want to cover a large area, let's say the mine site, in order to include stockpile calculations, deformation monitoring, and other aspects, well, yes, please calibrate your cameras. And of course, if you have 3 drones, it means you have to do 3 camera calibrations. You can put this all in a big bundle adjustment. If you have more cameras, you actually should get better results, because you can also you can add constraints to the adjustment. For example, object points are the same in 3 different cameras, images from 3 different cameras, so you can add many more constraints to the least-square adjustment. But again, it comes back to what you want to achieve, and based on what you want to achieve, you have to put the workflow into place. I think it's an exciting new field, and I think there are lots of applications, but I don't see the application really in the high geometry aspect. I see it more in the remote sensing aspect, where maybe 5 centimeters do not matter, or in the rescue mission where actually 5 meters do not matter.
Camila, could you read the next one?
From Alan Salomon, impressive talk, Petra. May I ask which public data sets are available from RPAs for teaching and research purposes?
That's a very good question. It's an excellent question. All right. First of all, lots of the software companies provide you with some of the data sets, some images, so you can use them in order to do your own kind of processing and evaluate outputs. I think one of the and I have to double check. I should have double checked this before the talk. I apologize. I forgot. The in Germany, a former mine site in Söllern is being established as a calibration field, and this area have been used by a number of different researchers within Germany, from Hamburg and Brunswick and so on. And they captured images of this field with different cameras. I believe that this is part of an ISPRS initiative, and maybe one of the other panel members can answer this question if you know the answer. and I would have to double check if it's possible to get access to the images. But I think my first point of call would be the benchmark pages from ISPRS, but also from IEEE. And then if normally researchers are happy to share images as well. So if you find one very good paper where you think you want to try your approach on it, I think it's worth to just get in touch with the other researcher. But I think there are areas where they want to try to create a benchmark data sets, but yes, it's difficult. It's difficult also because different flight heads can have different impacts and so on. But yeah, try the benchmark pages of ISPRS and IEEE first, I would say.
Professor Mitishita, could you read the next one?
The question from Mark Szymowski. For DTM generation, there is some innovation with photogrammetric data.
I'm not sure what photogrammetric data in this context means. With DTM generation, yes, of course, there's a huge community, research community. And why we have a PhD student online working in the area of structure for motion. There are lots of, so we had the same global matching with the dynamic programming. There are lots of researchers who work in try to improve the DTM generation, the dense matching. It's a big community within IEEE and other societies as well. I'm not quite sure how photogrammetric data relates to the DTM generation. The DTM generation often uses computer vision approaches. There are lots of computer vision people doing research. If it's meant of marrying to marriage photogrammetry with computer vision for dense matching, dense matching needs good parameters of the X orientation of the camera. Yes, so if you have better input data, you most likely will get better DSM models. But yeah, I'm a bit unsure how to answer that. I apologize for that.
We are going for the final questions. There is one from Jose Marcato. Is there any open source software for UAV photogrammetry that has been used with competitive results compared to commercial softwares?
I would like to answer this question in two steps. First of all, competitive results to open source solutions like Pix4D and Agisoft. Pix4D and Agisoft are used by many people. They're very powerful softwares, but it depends on what you want to achieve. Okay, so if you want to achieve precise measurements for deformation analysis, for example, so again, what you want to do, I would not suggest to use it for deformation analysis. I would go to other software products such as this ADAM technology or Australis, where the geometry aspect has a higher weight. Is there open source software available? I think there are lots of platforms where you can upload online your images and have it processed. I don't have them in my mind, in my head. I would have to look it up. OpenCV has a huge library which can be used. MATLAB has a huge library which can be used. There are lots of structure for motion implementation, visual SFM, for example, which are open source, which can be used as well. So yes, there are heaps of open source softwares available. They're not push button exercises. You actually have to understand what's going in the background, but I think that's actually of advantage. Maybe if one of the other panelists wants to add to this, but to answer the question, yes, heaps of them available. The one which comes straight to my head is OpenCV and Visual SFM. and you can achieve very good results, but you have to be a much more of an expert in order to do so.
Perfect. Well, there is a question here from Antonio Tomaselli. He has a concern of the level of accuracy needed when acquiring very high spatial resolution images. For instance, with 1 centimeter GSD, it will be quite difficult to achieve such an accuracy with onboard GNSS and even in the GCPs. What could be the solution for this paradox?
I would say, first of all, if Antonio was not able to answer that, I think I won't be able to answer that. I think one of the experts is talking there. What I can take away from the talks which I was listening in, for example, Clive talks, is at some even if you have the GPS and ground control points, I think what we maybe have to rethink is the weighting, what we put into the least square adjustments. So if we, for example, if you have a very low ground sample distance, meaning that the type points we created have an incredibly low standard deviation. And if we apply the rule 0.2.5 times ground sample distance times the height to base ratio, the standard deviations will be very, very small for our type points. If the standard deviations are very, very small, meaning that our weights which we introduce for those into the least square adjustment will be very, very high. So I think if we try to go back to the basics of least square adjustment, just to try to look more of how the least square adjustment works and how to introduce the different weights, I think that would be one possible way. But again, if Antonio couldn't have answered it yet, I think much more research will be required to answer this question.
Perfect. Professor Mitishita, please.
This question from Leonardo Biffi. Nice presentation, Professor Petra. One question. Using SFM for close range, smaller 5 meters, terrestrial photogrammetry, is it the use of calibration and grounded control points important?
Well, the ground control points will be important to scale. If you have 5 meters and less, you can consider alternative methods to scale, for example, scale bar. What I suggest, if you do close range photogrammetry less than 5 meters, that you pre-calibrate your camera. So you have, for example, a fixed calibration field, or there's this kind of cubes which you can create yourself, which you can just plaster with control points. So I would say use a very good calibration field to pre-calibrate your camera. Then, of course, make sure that nothing changes, and then to take your close range object, to capture the close range object, and then to scale it, maybe use alternatives to ground control points. For example, use a scale bars or other objects for scaling your terrestrial point cloud. And especially close range, calibration becomes more important because the errors introduced can become much quicker, bigger.
Perfect. Camila, could you read the last question?
From Ju Del Pizol. Consider a student with some ability with drone interested in deep learning. Please provide some advice where to start working with this and what are the basic requirements. Thank you.
All right. I'm not sure what your background is, Joel. I don't know if it's the computer science part, or is it the surveying part, or is it another another background you have. Well, my talk was more on the geometry aspect, and deep learning is used especially for example, classification or some if you have deriven data from your drone data set, and then you try to apply deep learning to it, for example, with the NDVI and the crop health, a prediction of crop health. So I think there are actually two different kinds of boots. So one is more the drone and data capturing and pre-processing, and then the deep learning is for me more the post-processing. And post-processing, yes, for crop health. So I do some work related to health, so try to analyze the phases. And what's the best way to start? Deep learning is a huge, big field. If you're interested in deep learning, I believe listen to Jan Dirk Begner's talk, which were given as part of the series, and listen to some of the other talks to get a rough idea of what you can achieve and how you can achieve it, and then from there maybe to get further inputs of how to work in this field. It's a big field, so it's not quite easy to answer, say, read book A or B, because the books are out of date by the time basically they are circulated. Yes, so it's short answer, I think, two different boots. One is the drone capturing, and one is then the post-processing and the AI aspect. With the AI aspect, try to listen to some talks in this area. I apologize, I can't give a more detailed answer to that.
Perfect. Well, I think with that one we finish actually the discussion section. We have here participants from Brazil, Ecuador, El Salvador, Japan, Malaysia, Mexico, Norway, USA, Peru, and Bhutan.
That's excellent.
Quite impressive.
Very expressive, and for the person in Norway, it's in the middle of the night, so that's very, very appreciated.
Yeah. Well, thank you again in the name of the Brazilian chapter of the Geoscience and Remote Sensing Society, actually, for accepting and making available your precious time to share actually your knowledge and your patience with us. That's very highly appreciated. Professor Mitishita and Camila, if you also have some final words, then we can close actually this
okay.
webinar.
Thank you very much, Professor Petra. It's very nice, interesting talking. I hope next time you have opportunity to stay here in Brazil with us. Thank you very much.
Yeah, thank you, Professor Petra. It was a wonderful presentation.
Thanks a lot for the invitation, and I hope that I can visit Brazil at one stage, and one of your favorite drinks is one of my favorite drinks as well. So let's catch up for caipirinha.
Okay, perfect, wonderful.
Okay.
Thank you again, and then with that we close actually this webinar, and wish you actually all pleasant actually week and a nice weekend that is actually approaching. And since this is the last talk, don't forget actually to fill the quiz that we have. And the certificates will be sent actually by email. And well, yeah, I will actually close actually the transmission. If you can just stay a little bit more for the final pictures, I would thank tremendously. Yeah.
I would like to add one thing. If you're interested as a PhD student who were listening today in one of the talks, please send me an email. I will be able to give you access to the talks for free. and please spread the words. And I'm sorry, I should have mentioned this earlier. I apologize for that. But yes, if you're interested, please email me. You will be able to access them for free.
This will be wonderful. Yeah, I think it's a wonderful material available, and I think it will be interesting for those students, bachelor or master or even PhD, actually to have access actually to this material. Thank you again, and then with that we close actually this webinar. Bye bye.
Bye.
See ya.